Have you ever wondered why a metal spoon gets hot when you stir your coffee, or how a radiator warms your room in winter? The answer lies in the fascinating world of heat transfer. Heat transfer, in essence, is the movement of heat from one place to another, a process that's constantly happening around us and within us. It's the reason why we can feel the warmth of the sun on a clear day, or why a metal bar can be heated from one end to the other. It's an invisible yet vital process, a key player in the performance of everyday objects and high-tech devices alike. Now, heat doesn't just jump from one place to another. It follows certain mechanisms, and three of them are primarily at work here: conduction, convection, and radiation. Each of these mechanisms has its unique characteristics and applications, and together they weave the intricate tapestry of heat transfer. Conduction is the process through which heat travels through solids like an iron rod or your coffee spoon. It's the reason why the handle of the spoon gets hot, even though it's not directly in contact with the hot liquid. Convection, on the other hand, is the mechanism through which heat circulates through fluids like air or water. It's the reason why you feel warmer when you stand near a heater, or why a pot of water boils faster when it's stirred. And finally, there's radiation, the only mechanism that can transfer heat through a vacuum. It's the reason why we can feel the heat of the sun millions of kilometers away, and why a campfire warms you even if you're not directly above it. Understanding these mechanisms of heat transfer and how they interact is more than just an academic exercise. It's an exploration into the fundamental principles that govern our universe and our daily lives. So buckle up as we embark on this journey to unravel the mysteries of heat transfer. Imagine you touch a hot pan with your hand. Instantly you feel the heat. That, my friends, is conduction at work. Conduction is the silent traveler of heat, a fundamental mechanism of heat transfer that involves the exchange of energy between two solid objects in direct contact. Picture that hot pan again. The heat from the pan travels to your hand, not through any liquid or gas, but through the solid molecules of the pan and your skin. What's happening here is a fascinating dance of energy. The hotter molecules in the pan, jiggling with more energy, collide with their cooler neighbours, passing on some of their energy in the process. This energy transfer continues from molecule to molecule, from the hot pan to your hand, making you feel the heat. But how do we quantify this heat transfer, you ask? Enter Fourier's law, a cornerstone of heat conduction. Named after the French mathematician Jean-Baptiste Joseph Fourier, this law gives us a mathematical way to analyze conduction. In its simplest form, Fourier's law states that the rate of heat transfer through a material is proportional to the negative gradient in the temperature and the area through which heat is transferred. Picture it like a crowd at a concert. The greater the difference in temperature, like the difference between fans at the front and the back, and the larger the area of contact, like the size of the crowd, the more rapidly heat will be transferred. So if you've ever wondered why metal feels colder than wood, even at the same temperature, it's because metals are better heat conductors. They transfer heat to or from our skin more rapidly, making them feel cooler or hotter. And that's how heat silently travels through solids from a region of higher temperature to a region of lower temperature. This is the essence of conduction, a process that's happening all around us all the time, shaping our experiences in ways we often take for granted. So the next time you touch a hot pan or a cold piece of metal, remember, you're feeling the silent traveler of heat at work. Scene script. Ever noticed how a pot of water starts to circulate when you heat it? That's convection in action. Now let's dive into this fascinating mechanism. Convection is the heat transfer that occurs in fluids, such as gases and liquids, through the movement of bulk matter. It's like a fluid messenger, carrying thermal energy from one place to another. Imagine a pot of water on a stove. As the bottom layer of water heats up, it expands and becomes less dense. This less dense, warmer water then rises to the top, displacing the cooler, denser water, which sinks to the bottom to be heated. This creates a circular motion, or convection current, that effectively distributes heat throughout the pot. But how does this apply to our everyday life, you might wonder? Enter heat exchangers. These are devices designed to facilitate the efficient transfer of heat from one medium to another. They are the unsung heroes in many of our everyday appliances, from air conditioners to refrigerators, and even in our cars. Heat exchangers come in different types, each with their unique characteristics. Take the tubular heat exchanger, for instance. It's simple in design, with one fluid flowing inside the tube and the other around it. The two fluids are separated by the tube wall, allowing heat to transfer without the fluids mixing. Then there's the plate heat exchanger. It's a bit more complex, with a series of thin plates stacked together. The fluids flow between these plates, allowing for a large surface area for heat exchange, making it highly efficient. But what's really cool is that these exchangers can work in two ways: parallel flow and counterflow. In parallel flow, the two fluids move in the same direction, while in counterflow they move in opposite directions. Counterflow is generally more efficient, as it can achieve a greater temperature difference between the fluids. So, the next time you see water boiling or feel the breeze, remember, it's convection doing its magic. How does the sun, millions of kilometers away, warm our planet? The answer is radiation. Radiation, the invisible heat transporter, is an intriguing phenomenon. Unlike conduction and convection, it doesn't need a medium to transfer heat. Instead, it uses electromagnetic waves to transport energy across vast distances. Imagine this. The sun is about 150 million kilometers away from us. There's no solid, liquid or gas connecting us to the sun. Yet, it manages to keep us warm and toasty. That's the power of radiation. Let's delve a bit deeper into the science behind radiation. We have something called the Stefan-Boltzmann law. This law states that the total energy radiated per unit surface area of a black body is directly proportional to the fourth power of its absolute temperature. Simply put, hotter objects radiate more heat. This brings us to another fascinating concept, the Stefan-Boltzmann constant. This refers to the proportionality constant in the Stefan-Boltzmann law. It's a tiny number, around 5.67 times 10 to the negative 8th power in standard units. However, this constant is essential in calculating the amount of energy radiated by an object. Now let's talk about Kirchhoff's law. It states that for an object in thermal equilibrium, the emissivity is equal to the absorptivity. In other words, an object's ability to emit radiation is equal to its ability to absorb it. This law is vital in understanding how objects interact with radiation, both emitting and absorbing it. Lastly, let's touch on the applications of these principles. They are used in a variety of fields, from designing solar panels to predicting climate change. Understanding radiation helps us harness the sun's energy and protect our planet. So, despite being invisible, radiation plays a crucial role in warming our planet. Now that we've decoded the three mechanisms of heat transfer, let's connect the dots. We've journeyed through the fascinating world of heat transfer, from the silent heat traveler, conduction, where heat moves through solids, to the fluid messenger, convection, where heat is transported by liquids and gases, and finally, the invisible heat transporter, radiation, where heat travels through nothingness itself. Recall the first mechanism, conduction. It's like a silent whisper passing from one molecule to another without any actual movement of the particles themselves. This is why you can hold one end of a metal rod over a flame and soon feel the heat on the other end. Fourier's law quantifies this process, giving us a way to predict and understand how quickly heat will be conducted. Next, we dove into the world of convection, where heat rides on the waves of fluid motion. It's the reason why boiling water stirs itself and why warm air rises above cooler air. Convection is also the mechanism at play in heat exchangers, devices designed to efficiently transfer heat from one medium to another. Whether they're tubular or plate exchangers, their design principles hinge on maximizing convective heat transfer. Our journey concluded with radiation, the only method of heat transfer that doesn't need a material medium. It's how the sun warms our planet, and it's governed by laws like the Stefan-Boltzmann's law and Kirchhoff's law. These laws help us understand how objects absorb, emit, and reflect radiant heat. These three mechanisms, though distinct, are interconnected, often working in tandem. When you boil water for tea, conduction heats the pot, convection stirs the water, and radiation warms your hands as you hold the cup. It's a symphony of heat transfer happening in your everyday life. So, the next time you feel warmth from a heater or a cool breeze, remember the science behind it. And don't forget to subscribe for more, because you won't find me later.